A comment from teacher Carlos, straightforward of Durham College. I've spent my whole life constructing a specific perspective on the world, and now that thought is being addressed, I invite it since it is how we advance in science. James Webb is toppling nearly everything in cosmology that has been acknowledged as obvious for as far back as century. Another ultra-profound picture affirms that we have made mistakes in space science. The telescope that should uncover to us the first stars of the universe is annihilating the earlier perspective and may introduce a new science. Not all analysts are frightened by the new data. Numerous scientists welcome the progression since it has long been obvious that something was amiss with our past speculation. The irregularities in estimating the universe's expanding speed ought to have awakened scholars long ago. Rather than properly perusing the signs, they stuck to obsolete thoughts. The astronomical microwave background radiation (CMBR) is thought to be the most established in the universe. The CMBR was shaped around 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to form stable hydrogen molecules. Scientists refer to this change as reionization, and it made the universe penetrable to light. The CMBR was discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were fostering another type of receiving wire. They saw a consistent commotion coming from all directions overhead. This revelation was for some time viewed as one of the most convincing bits of proof supporting the theory of the prehistoric cosmic detonation. Penzias and Wilson shared the Nobel Prize and made history in astronomy. The CMBR most likely gives a brief look at the youthful universe. Small temperature changes give critical data about the conditions in the universe soon after the Big Bang. Scientists utilized the CMBR to quantify the universal expansion rate, among other things. Edwin Hubble, a cosmologist, had proactively made this calculation in the last part of the 1920s. Hubble found that far-off universes recede from us this way, and that with speed corresponding to distance. Today we allude to these estimations as the Hubble rule or the Hubble constant. Hubble didn't yet have the high-level estimation techniques that were utilized many years some other time when the CMBR was found. Specialists recalculated the rate, and the new figure is considerably lower than Hubble's original estimate. Later scientists recalculated the rate utilizing type cosmic explosion as the standard candles. Stargazers approached such steady light that it very well may be used as a reliable measuring point. The error in deciding the universe's expansion rate has existed since the 1990s. From that point forward, scientists have known, or rather thought, that something was off with the evaluation of the CMBR, the estimating techniques, or the idea of infinite development. The S8 strain or Hubble pressure alludes to the distinction between the different estimated dimensions of the universe's expansion rate. This has broad repercussions past a simple measurement difference. The numerous disclosures uncover significant insights into how we have previously perceived the universe. For quite a long time, scholars were confused since its beginning. The James Webb Space Telescope has given scientists some startup outcomes, which may now illuminate the problem of the universe's expansion rate. Universes are so old and mature that their beginning probably happened before the Big Bang. There could be no longer discussed measurement irregularities, rather scholars are discussing the most challenging issue in contemporary stargazing. Not exclusively could the universe's expansion speed be mistaken, but the entire concept of expansion or the Big Bang is being reconsidered. Webb's photographs uncover evidence of a world that is immensely different from what we have long accepted. The strain served as a first advanced notice, and all specialists who keep on trusting in obsolete speculations presently face a test. Do we indeed know nothing about the universe? Numerous scientists are presently remaining on the rubble of their all-consuming purpose, gazing into space despondently and incapable of understanding the way things are. Given the ongoing logical quandary, we should ask ourselves, what do we really know about the universe? To address this question, we should initially get a handle on how science works. Theoretical researchers utilize a convoluted organization of numerical models, experimental information, and rational thinking to arrive at discoveries. Going from general to explicit, their expertise depends on a blend of noticed occasions, test information, and broad hypothetical investigation. The name hypothesis alone shows that these are creations and thoughts, not reality. We just have reasonable information as pictures from telescopes, sound waves, and radiation caught by radio telescopes and the latest information from neutrino measuring frameworks or gravitational wave identifiers. With the James Webb Space Telescope, we currently have a gear at our disposal that permits us to break down the earliest light into person frequencies and dissect it in manners that were previously unthinkable. Webb can show us which elements were common in worlds a long time ago, how much mass was contained, and the number of stars. This shows the telescope can modify a system's structure and course of travel. However, Webb might have blemishes in a portion of his photographs. In view of enormous growth plates, the telescope can't tell us whether we are checking out worlds or dark openings that sparkle as brightly as worlds. We should confront the way that our science has long acknowledged an excessive number of potential results as realities while overlooking other option explanations. Research has for quite some time been sure that it is correct. The latest discoveries from the James Webb Telescope give essential signs to replacing thoughts with new insights. As has happened many times in science, researchers are as of now holding up for the new results, which are extremely peculiar, and it seems unimaginable for some analysts to concoct new interpretations at the present time. The new disclosures are testing the premise of present-day physical science, which panics numerous researchers. The present physical science courses are generally founded on Isaac Newton's revelations in the 17th century. For quite a long time, his standards of motion and gravity filled in as the foundation for our physical comprehension of this current reality, including the universe. Newton's standards made sense of the developments of items under normal circumstances and functioned admirably on Earth. In space, however, his ideas required to have been extended, which Albert Einstein considerably refined at the turn of the 20th century. His extraordinary hypothesis of relativity published in 1905 changed our perspective on reality. Einstein exhibited that space and time are connected with each other and rely upon the movement of the observer. The general hypothesis of relativity, published in 1915, extended the idea by giving numerical proof of gravitational peculiarities in light of the curve of spacetime brought about by masses like stars or systems. Einstein's hypotheses and ideas were by and large firm, yet he moved toward his cutoff points throughout his life. The specialist knew that his hypothesis could never be adequate to depict the entire universe. He would have liked to find the world's equation, but he did not succeed. Strangely, no other scientist has prevailed right up till now. Where's the mix-up? Wouldn't it be interesting to know where the slip-up is? Makaku, a noticeable space expert from the US, expressed in a meeting that the individual who responds to this challenge will undoubtedly win the Nobel Prize. Let us explore what realities researchers might have overlooked, where they may have misinterpreted occasions, and whether our telescopes are to blame. Dark matter and dark energy are among the most logical wellsprings of the infinite disaster. Our ongoing hypotheses of the universe consolidate the possibility that dark matter and dark energy together account for around 95% of the universe. However, neither has at any point been straightforwardly seen, and thus, their actual presence has never been laid out. Possibly they don't exist at all, and we must make sense of the universe's development and system dynamics independently. Or both have characteristics that we don't yet figure out. One hypothesis now being talked about is that the physical properties of the two dim parts have evolved after some time, which could imply that we are managing some type of insight. The next thing to be pried is gravity. This power, which probably causes fascination or curve in spacetime because of mass, still can't seem to be shown. Einstein is fundamentally answerable for the idea of spacetime curve, which has been over and over demonstrated right. Anyway, we can't preclude the likelihood that gravity has completely various characteristics than recently suspected, or that the gravitational power between objects is brought about by an alternate component. Some values, known as inestimable constants, have been laid out in current cosmology and astronomy throughout the long term. These qualities are generally dependable on the grounds that they seldom change. Estimations have uncovered that slight vacillations in these implied constants present new energy into the universe, permitting us to make sense of different occasions. Without the presence of dark energy, it is too conceivable that our understandings of the red shift of light are wrong, and that we have been estimating erroneous distances inside the universe and deciding universe's ages for a really long time. Maybe our convictions about the universe's unique state were moreover mistaken. We might have misread the inestimable microwave background radiation. It's additionally conceivable that the universe can't be followed back to a solitary beginning point. This would suggest that the theory of the universe's origin is incorrect. In spite of the fact that we have modern innovation, we can't preclude slight mistakes in the Webb telescope or other observational instruments. In the middle of the emergency, engineers and researchers concurred that blunders in instrumentation, information handling, and interpretation are continuously conceivable. The area of cosmology remains at an intersection today where the foundations laid over hundreds of years are being tested by novel perceptions and information from cutting-edge instruments like the James Webb Space Telescope (JWST). These difficulties not just inquiry laid out speculations but additionally open up roads for altogether new understandings of the universe and its beginnings. One of the central mainstays of modern cosmology is the idea of the Big Bang, which suggests that the universe began from an infinitely dense point and has been expanding since. This theory has been supported by various lines of evidence, including the cosmic microwave background radiation (CMBR), the Hubble constant measurements, and the distribution of galaxies across the universe. The discovery of the CMBR in 1964 was a turning point in cosmology. It provided strong evidence for the Big Bang theory by showing a uniform glow of radiation across the sky, believed to be the glow of the hot, dense early universe when it first became transparent to light. This artifact radiation has since been widely considered to understand the origin, age, and structure of the universe. However, recent observations and measurements, particularly from the JWST, have posed significant challenges to this established framework. The JWST, with its phenomenal sensitivity and resolution, has begun to reveal galaxies and phenomena that defy traditional explanations. For instance, the discovery of galaxies that appear to be unusually old raises crucial questions about the timeline of cosmic evolution and the processes leading to the formation of stars and galaxies. In addition, discrepancies in the measurement of the universe's expansion rate, known as the Hubble tension, persist despite decades of refinement in observational techniques. While CMB-based measurements suggest a certain rate of expansion, independent measurements using type Ia supernovae as standard candles yield slightly different results. This discrepancy suggests possible flaws in our understanding of either astronomical distances, the nature of dark energy driving the universe's acceleration, or both. Dark matter and dark energy remain enigmatic components of the universe, constituting the vast majority of its content yet eluding direct detection. These mysterious substances are invoked to explain observed gravitational effects on galaxies and the accelerated expansion of the universe, respectively. However, their exact nature and properties continue to elude scientists, leading to various theoretical and experimental efforts to uncover their identities. Beyond these theoretical challenges, the JWST has provided stunning direct evidence of anomalies that challenge our current understanding of cosmic history. Images of distant galaxies, some of which existed just a few 100 million years after the Big Bang, suggest a complex and rapidly evolving early universe that may require new theoretical frameworks to fully comprehend. The JWST's ability to analyze the spectrum of light from these ancient galaxies offers insights into their chemical composition, star formation rates, and even the presence of heavy elements crucial for planet formation and life. These observations not only refine our understanding of galaxy formation but also raise intriguing questions about the conditions under which life could emerge in the universe. Furthermore, the concept of the Big Bang, which posits a rapid, remarkable expansion of the universe following its inception, remains a subject of debate and investigation. While inflationary models provide a robust explanation for the observed large-scale structure of the universe and the uniformity of the CMB, alternative theories that do not require inflation are actively pursued to reconcile theoretical discrepancies and observational challenges. In conclusion, while the challenges posed by the JWST and other cutting-edge instruments may disrupt established theories, they also present extraordinary opportunities to expand our understanding of the universe. By embracing these challenges and pursuing rigorous scientific inquiry, astronomers and cosmologists are poised to uncover new insights about the universe and our place within it. The journey ahead promises to be both thrilling and transformative as we continue to unravel the mysteries of the cosmos and push the boundaries of human knowledge.